In the previous video, we saw how we could relate the edges and angles of an arbitrary triangle using the sine trigonometric function, and that gave us the sine rule. In this video, we're going to again be relating the edges and angles of an arbitrary triangle, but this time we're going to look to do so using the cosine trigonometric function. This is going to give us the cosine rule, which can be applied to slightly different scenarios than the sine rule, as we will later see. So just as we saw how useful the sine rule can be in the previous video, the cosine rule is equally as useful. It forms a different set of relationships which allows us to solve slightly different problems. Thus, by using the sine and cosine rules together, we can solve a much greater range of problems than if we only had one rule or the other. So let's start out by drawing an arbitrary triangle exactly as we did in the previous video. So we can draw out an arbitrary triangle very similar to the diagram that we had when we were proving the sine rule. And just as when we were proving the sine rule, we're going to need to name our edges and angles in this arbitrary triangle, and they're going to follow the exact same naming convention as we had with our sine rule. So if you recall, that naming convention is that edges have lowercase letters, so I could call this edge A, this edge B, and this edge C, and angles have uppercase letters such that the angle that sits opposite an edge shares the same letter as it. So here, this angle sits opposite lowercase a, therefore it's going to be uppercase A. This angle sits opposite lowercase b, therefore it's going to be uppercase B. And this angle sits opposite lowercase c, therefore it is uppercase C. Now, just as we did when we were proving the sine rule, we can create a line from our angle C down to our edge C such that it intersects that edge at a right angle. What that's going to do is it's going to split our arbitrary triangle into two right-angled triangles. And as we've seen many times now, we're able to apply a number of theories to right-angled triangles that allow us to relate various pieces of information of the arbitrary triangle. So I'm going to label this new edge as H. It sort of represents the height of our triangle, if you will. And the new point that we've just created, I'm going to label as D. Now, so that this doesn't get too cluttered and confusing, I am going to move C, which of course is the edge of our arbitrary triangle, this entire edge. I'm going to move that just down here. So just remember, C is, of course, this edge, the entire edge. Now, in this case, I need to know, and we're going to see why we need to know in a second, I need to know the length of this edge and the length of this edge. But we don't know the lengths of these edges because we split our arbitrary edge C, and because it's an arbitrary triangle, we have no idea where point D is going to lie on our edge C. So I'm going to need to introduce a new variable. It's some value that we just don't know the actual value of, but it's going to help us to be able to relate the two edges that we've just defined. So the first edge, this edge on the left, I'm just going to simply call X. It's a new variable. We don't know how long that edge is. We don't know the value of X, but we know that we have this edge and it has some length, and that length is going to be represented by the variable X. Why are we calling this edge X? Well, it's going to allow us to write the length of dB, the length of this edge on the right, in terms of the length of C, the entire length, and the length of AD, which we know now is X. Because if this is the entire length, to get the length of just this edge between dB, we need to subtract from the entire length the length of X. So hopefully you can follow that dB is going to have a length of C minus X. Now that we've got all of that in place, we're going to analyze these two right-angled triangles. Of course, the first right-angled triangle is ACD, the second is BCD. We're going to analyze both of these triangles. Now, in both cases, we're going to use Pythagoras' theorem to relate the edges of the triangles. Also, in the case of ACD, we're going to use our cosine trigonometric ratio to form some relationship that involves the cosine of an angle and some of the edges in that triangle. And again, that's the whole purpose of this video, is to determine some relationship between the edges and angles of an arbitrary triangle by using the cosine trigonometric function. So if we apply Pythagoras' theorem to ACD, we're going to see that x squared plus h squared is equal to the hypotenuse, which is b squared. So x squared plus h squared is equal to b squared. Nothing complicated there. We've simply used Pythagoras' theorem that we covered in great detail back in volume 1. We can do the same thing to b, c, d. In this case, we're going to have this edge, which is c minus x. So c minus x, all of that squared plus h squared is equal to, and the hypotenuse of this triangle is a, so it's equal to a squared. Now, since we have this in parentheses, I do want to expand this entire equation. So this is going to become c minus x plus h squared is equal to a squared. So this is going to become c times c, so c squared, c times minus x, so minus cx, minus x times c, so minus xc, and minus x times minus x, that's going to become plus x squared, plus h squared is equal to a squared. And we have minus cx and then minus xc. Both of these are the same value, therefore this is going to become c squared minus 2cx plus x squared plus h squared is equal to a squared. So that's applying Pythagoras' theorem to both of the right-angled triangles we've just created. As I mentioned a second ago, I also want to relate this right-angled triangle using the cosine ratio. Now, the only angle in this right-angled triangle, other than the right angle, of course, that we know is angle A. We don't know the angle up here because it's not the entire angle C. It is some portion of angle C, and we have no idea how big that angle is because we don't know, due to the fact this is an arbitrary triangle, how this line is going to relate to the angle C. Therefore, we're going to be relating our angle A, and we know that our cosine ratio is that the cosine of an angle is equal to the equal to the adjacent over the hypotenuse. So the cosine of an angle is equal to the adjacent over the hypotenuse. Well, in this case, we're dealing with angle A, so the cosine of angle A is equal to the adjacent, here is our x, and the hypotenuse is b. So the cosine of A is equal to x over b. Allow me to rearrange this to find the value of x. So x is equal to b cosine of A. Now you may ask yourself, well, why have we done all these equations? We seem to have some equations all over the place. We've got two equations that came from Pythagoras' theorem, one here and one here, and then an equation that uses the cosine trigonometric function. Will allow me to rewrite two of these equations down with our trigonometric equation, and you're going to see exactly why we have taken these steps. So the first equation was x squared plus h squared is equal to b squared. So x squared plus h squared is equal to b squared. And then our other equation here is c squared minus 2cx plus x squared plus h squared is equal to a squared. Now, if we just focus on these three equations for a second, what you're going to notice is that here we have x squared plus h squared. Well, notice we also have x squared plus h squared up here, so we can replace this part of our equation with b squared, which we know. We don't actually know we don't actually know x, but we do know b, so we can replace part of this equation. So c squared minus 2cx plus b squared is equal to a squared. You can also see that we have here a value of x, again, that we don't know, but up here we're saying x is equal to b cosine of a, so we can replace our x with this other value, and it's going to give us an equation in terms of things that we know from our arbitrary triangle. So c squared minus 2cb cosine of a plus b squared is equal to a squared. We can tidy this up just a little bit to get it into a slightly clearer form. So I'm going to say a squared is equal to b squared plus c squared minus 2bc cosine of a. This right here is our cosine rule. Now there are a few things to note with our cosine rule. Firstly, let us take a second to discuss the differences between the sine rule and the cosine rule and understand why they complement each other for problem solving. So if you recall back to the previous video, our sine rule is a over the sine of a is equal to b over the sine of b, which is equal to c over the sine of c. Now with our sine rule, if we wanted to find the length of an edge, we can do that as long as we know the angle opposite that edge on one other edge-angle pair. Likewise, if we wanted to find an angle, we could do that as long as we knew the edge opposite that angle, and again, one other edge-angle pair. The cosine rule, however, lets us find the length of any edge if we know the length of the other two edges and any single angle in our triangle. Now granted, it is easier to find the length of an edge that is opposite the angle that we know, because it's easier to rearrange this to solve for A than it is to rearrange this to solve for B or C, but it can be done. You can rearrange it to solve for any edge. Therefore, we can find any edge as long as we know the other two edges and any angle in our triangle. Unlike the sine rule, which to find an edge, we need to know at least two angles in our triangle, and one of those angles must be the angle opposite the edge that we know. Also, to find an angle with our cosine rule, all we need to know are the lengths of all three edges, whereas with the sine rule, we needed to know at least one other angle, and we needed to know the length of two edges that are opposite the angle that we know and the angle that we're trying to find. So each rule has its uses, and when approaching a problem, it's really worth seeing if we can apply one of these two rules to find the information we require, because obviously they each require different combinations of information to find different angles or edges, and because of that, one may be applicable to a problem where the other might not. So it's always worth seeing, can we apply the cosine rule? Maybe, maybe not. Can we apply the sine rule? Maybe, maybe not. And more times than not, you'll find that one of these two rules will allow you to find the information you're after. Other things to note, you may find that different textbooks and maths resources write our cosine rule in slightly different ways. They're all the exact same formula, they might just be rearranged differently. For example, to have a squared, b squared and c squared on one side of the equation and our 2bc cosine of a on the other side of the equation, for example. They are the same rule, they've just been rearranged, so hopefully everyone's very comfortable with rearranging equations and can see they are actually the same, they've just been written slightly differently. Also, because our triangle is completely arbitrary, the letters in our cosine rule are interchangeable. So all that actually matters is the relationship between the angle that we know or that we're trying to find and the edge that is opposite that angle. So you notice it is, if we're using angle A, it is the edge opposite the angle that we're using or finding squared is equal to the other edge squared plus our final edge squared minus 2 times our other edge times our final edge times the cosine of the angle. So the important thing is, if our angle is the angle that we're finding or the angle that we're using, the edge that is opposite it must be edge A, and the other two edges become B and C. Now finally, as with our sine rule, there is actually another case that we would need to examine to fully prove our cosine rule, and that's the case where, if I just quickly sketch a triangle, I'm not going to use the line tools here, that's the case rather where when we drop that perpendicular edge down, it sits outside the original triangle. We would actually need to look into and analyze this case to fully prove our cosine rule. Now in the previous video I did show the entire proof, and that was to help us practice trigonometry. In this video, showing the full proof really doesn't get us using any more trigonometry than we've used until this point. So if you are interested in the full proof, you can find it very quickly if you just search on the internet for cosine rule proof, but I'm not going to actually go through the proof here on the whiteboard. If you do look into the proof yourself, you're going to see it's very easy to prove that this other case of triangle behaves in the exact same way and that our cosine rule is valid for any arbitrary triangle. Alright, so let's practice using our new equation. So I'm going to bring up a new whiteboard so that we have a nice clean page to work on here. and I'm going to work through a couple of examples on the whiteboard, and then I'm going to set a couple of questions for you to work through on your own. So let's start out by drawing a triangle. So I'm going to draw something like this. There we go. And we know some information about this triangle. We know that this edge has a length of 5, this edge has a length of 6, and this edge has a length of 3. And I'd like to use the cosine rule to find out the angle here that I've marked as theta. So if you recall, our cosine rule is a squared is equal to b squared plus c squared minus 2bc cosine of a. Now we're trying to find an angle using our cosine rule. That means that a must be theta, or theta must be a. It's our angle. And that means that this edge here must be our edge A, because it is opposite the angle theta. The other two edges, 5 and 3, can be B or C. They're interchangeable. It really doesn't matter as long as one of those is B and one of those is C. The important part is that our angle theta is A and our edge 6 is A. So as long as we keep that in mind, what we need to do is rearrange to find the angle A. So I'm going to start out by adding 2bc cosine of A to both sides of the equation. So we'll get a squared plus 2bc cosine of A is equal to b squared plus c squared. I'm then going to subtract a squared from both sides. So 2bc cosine of A is equal to b squared plus c squared minus a squared. Now we can see to get the cosine of A on its own, I'm going to need to divide by 2bc. So the cosine of A is equal to b squared plus c squared minus a squared divided by 2bc. And then finally, to get A, I'm going to need to use our inverse cosine function. So A is going to be equal to cosine to the minus 1, our inverse cosine function of b squared plus c squared minus a squared over 2bc. Now you'll notice, if you recall back to our inverse trigonometric functions video, the cosine inverse function returns an angle between 0 and 180 degrees. And therefore, because it returns an angle between 0 and 180, it's going to give us the single value for the angle that we're trying to find. Because we know all three edges, there is only one possible angle that will satisfy the angle for this triangle, because we know the lengths of all three edges. That defines an explicit triangle that has an explicit set of angles. And because of this, and because of the way the cosine rule is formulated, this is going to give us that single angle. Unlike the sine rule, where we're finding angles, and because of the way the sine rule is constructed, we have no guarantee that we have the correct angle, because sine returns between a negative 90 and positive 90, but an angle in a triangle can be between 0 and 180. Because the cosine rule returns between 0 and 180, it will only give us that single angle. So in this case, where we rearrange to find the angle, we're going to get the correct angle. There is only one value that satisfies that triangle. Okay, so we can put our values in. Again, remembering, of course, A is the angle we're trying to find, therefore the edge opposite that angle with a length of 6 must be our lowercase a. The other two edges can be B and C, it doesn't matter which is which. So A is equal to the inverse cosine of, so B could be, well, let's pick on 5 for B and 3 for C. So let's say it's equal to 5 squared plus 3 squared minus A was 6. Again, that's the important part. A is opposite our angle, so A is 6. Over 2 times B, which was 5, times C, which was 3. So if we work this out, we're going to get that A is equal to the inverse cosine of 5 squared is 25, plus 3 squared is 9, minus 6 squared is 36. 2 times 5 is 10, times 3 is 30. So A is equal to the inverse cosine of 25 plus 9 is 34, minus 36 is minus 2, over 30, which is going to be equal to the inverse cosine of minus 1 over 15. So we can use a calculator now to work out the value of A, which of course we know is theta, the angle we're trying to find. So A is equal to theta, which is equal to, if I bring a calculator up, I am working in degrees, so I'm going to take minus 1 divided by 15, so that's our ratio there, and I want to work out the inverse cosine of that ratio, so inverse cosine, and that's telling us that our angle is approximately 93.8 degrees. So our angle theta is approximately equal to 93.8 degrees. So you can see finding an angle when we know the three edges in the triangle is really, really easy with our cosine rule. The only thing we need to be careful of is the naming convention of our edges. We need to make sure the edge opposite our angle is named A, because our naming convention states the angle is capital A. Other than that, it's really very easy to use our cosine rule to find an angle. So that's finding an angle. Let's take a look at an example where we find an edge. So I'm going to bring up another new whiteboard. So let's hide out these guys, bring up a new layer, and I'm going to start out by drawing a new triangle for us to work with. So I don't know, something like this, and a layer to draw on. And in this case, we know this edge is 8 units long, this edge is 7 units long. I'm going to say that this angle is 70 degrees, and I'd like us to find the length of this unknown edge. Now again, our cosine rule is a squared is equal to b squared plus c squared minus 2bc cosine of A. Now the angle, the only angle in this triangle that we know is that 70 degrees. So that's going to be the angle which gets a capital A. Therefore, if that's the angle that gets a capital A, the edge that we're trying to find is our lowercase a, and our edge of 8 and edge of 7 are going to be our B and C edges. It doesn't matter which way round we have those, but the important part is the edge we're trying to find is edge A. And that means rearranging this equation is going to become very, very simple, because we already have the only thing we don't know, A, on the left-hand side, and everything we do know on the right-hand side. So we simply need to take the square root of both sides to find the value of A. So A is going to be equal to the square root of B squared plus C squared minus 2BC cosine of A. Now, of course, when we take a square root, we could have plus or minus the square root, but we're finding the length of an edge, and that means we're only interested in the positive value that comes back from this square root, because it's a length, it therefore needs to be a positive value. So we don't need to worry about the fact that we could have a plus or minus square root. We are simply going to have the positive value. So now that we've got that, let's put our numbers into this equation. So we're going to find A, and A is equal to the square root of B squared. Well, I'm going to say that B is our edge with a length of 8. So it's equal to the square root of 8 squared plus C would be 7. So 8 squared plus 7 squared minus 2 times 8 times 7 times the cosine of our angle, which is 70 degrees. So if we start to work this out, it's going to give us A is equal to the square root of 8 squared is 64, plus 7 squared is 49, minus 2 times 8 is 16, 16 times 7 is 112, cosine 70 degrees. We can now simplify this a bit further, because 64 plus 49 is 113, minus 112 cosine of 70 degrees. I'm going to use a calculator now, so let's bring up a calculator. I'm first going to work out the value of 112 times the cosine of 70 degrees. So the cosine of 70 degrees, I am in degrees, so 70 degrees is 0.342. I can multiply that by 112, and that tells me that 112 cosine of 70 is 38.306, and then it keeps on going. So I'm going to copy this value now with Control C, and then I'm going to work out the entire value underneath the square root here. So to do that, I'm going to say 113 minus the value that I just copied for 112 cos 70. So if I paste that in and click equals, the entire square root under here is 74.69. So a is equal to the root of 74.69. So if I was to click the square root button here, it tells us that a is approximately equal to 8.64 units. So a is equal to the root of 74.69, which means that a is approximately equal to 8.64 units long. So that's how we find the length of an unknown edge when we know the angle that's opposite that edge. What we're going to be doing, or what you're going to be doing in a later question, is finding the length, or rather lengths, of an edge when we don't know the angle that's opposite that edge. We know one of the other angles. But that's coming up in a second. What I'd like you to work on first is going to be finding an angle in an arbitrary triangle. So let's bring up a new whiteboard for me to set you guys this question. So I'm going to bring up a new whiteboard, scroll on up to the top here. I'm going to start out by drawing a triangle. So the triangle I'm going to draw is going to look something like this. Fantastic. And let's bring up a layer that I can draw on. And this triangle has an edge of length 5, an edge of length 3, and an edge of length 6. Now you'll notice that this is the exact same triangle as we saw in an earlier example. However, this time I'd like you to find a different angle. I'd like you to find this angle here that I am marking as theta. So using the cosine rule, find the angle theta in that triangle. Go ahead and pause the video, give this an attempt on your own. Once you have a solution, or if you get stuck, unpause the video and I will work through the answer here on the whiteboard. Okay, welcome back everyone. So earlier we saw how we can rearrange our cosine rule to solve for an angle. Now I'm not going to go through the rearranging again, we've seen that already, but we saw that our angle is equal to the inverse cosine of b squared plus c squared minus a squared over 2 times b times c. So we saw earlier how we can rearrange our cosine rule to get an angle equal to the inverse cosine of b squared plus c squared minus a squared over 2 times b times c. Now we must remember, of course, we're finding this angle a. That means our angle theta is a, and that means our edge a is the edge that's opposite our angle, and that is the edge with a length of 3. So the most important part here is when we put our numbers into this equation, we make sure this edge, A, gets a length of 3. The other two edges are B and C. It doesn't matter which is which. I'm going to say the edge of length 5 is B, the edge of length 6 is C, but it doesn't matter which is which as long as we make sure that A here is the edge that is opposite our angle A. And that goes right back to the naming convention we used when we first proved our sine and cosine rules. So that means if we plug numbers into this, that A, our angle, which is equal to theta, is equal to the inverse cosine of B, I said was 5, so 5 squared plus 6 squared minus 3 squared divided by 2 times 5 times 6. Which means that theta is equal to the inverse cosine of 25 plus 36 minus 9 divided by 2 times 5 is 10 times 6 is 60, so divided by 60, which means theta is equal to the inverse cosine of 25 plus 36 is 61 minus 9 is 52 over 60. Fantastic. So we can use a calculator now to work out the value of theta. So if I bring up a calculator, so we need to take 52 and divide that by 60, and that gives us 0.866666 recurring, and then I'm going to use the inverse cosine to find out the angle theta. So inverse cosine to the minus 1, the inverse cosine, and we are of course in degrees, so that means our angle is approximately 29.9 degrees. So theta is approximately equal to 29.9 degrees. So hopefully you got the correct answer. If you didn't, just make sure that you were indeed using the correct equation to solve for the angle A. We saw this equation earlier, so maybe if you were rearranging the cosine rule yourself, just make sure you followed the steps correctly to get this equation. From there, make sure again that you identify if our angle is A. That means the edge opposite our angle, the edge opposite theta with a length of 3, must be this edge with a lowercase a. The other two edges of 5 and 6 are B and C. It doesn't matter which is which, but A must be 3. If you got that, just make sure that you did indeed work out the calculations here correctly to get the correct values. And if you did, you should have got an angle of 29.9 degrees. That's question 1. I'm going to set one final question for this video, but it is going to be a tricky one, so it's not going to be very easy for you. So question 2. So here is a triangle, something like this guy. Fantastic, and I need a layer to be able to draw on. So this edge here has a length of 10, this edge has a length of 11, and this angle is 50 degrees. What I'd like you to do is to use the cosine rule to find the two possible lengths of the edge I have just marked with a question mark. Now we know why there are two lengths, because it's a very similar problem to one that we saw in the video covering the sine rule. And we saw with the sine rule, when we have certain pieces of information but they don't fully define the nature of the triangle, in this case we don't know the angle here, which means of course this edge is free to rotate, and we don't know the length of this edge, and that means there's two possible triangles that satisfy the information we do know. So therefore there are two possible lengths for this edge. I'd like you to use the cosine rule to find the lengths of that edge. Now this problem is tricky, so please do take your time, and if you get stuck at any point, unpause the video. I'm going to work through the answer here on the whiteboard. So the best of luck with this, and really congratulations if you do make it all the way through and find the answer. Okay, welcome back everyone. So this question is a little bit trickier than our previous example of finding an edge, because we're not finding an edge that's opposite the angle that we know. If we remember, our cosine rule is a squared is equal to b squared plus c squared minus 2bc cosine of a. Earlier we saw trying to find an edge, but we were finding the edge opposite the angle that we know. Because of that, it meant we were finding edge a, and that simply meant we took the square root of both sides. Here, we're not finding edge A. Edge A has a length of 10. We're finding one of the other two edges. Now, we can name these edges however we like. We could say that this edge is B and this edge is C, or the other way round. I'm actually going to say that the unknown edge that we're trying to find is edge B, and that the edge that we know down here is edge C. So we're rearranging this equation not to solve for A, but to solve for B, and that's going to be a little more tricky. Now, as long as you take your time, as long as you're careful, and as long as you're able to see there's one particular step where you need to be able to recognize the form of the equation, and depending on how comfortable you are working with those types of equations, you may or may not have seen that step. But as long as you catch that step, everything's actually pretty simple. So I'm going to work through this. I'm going to try and work through it as slowly as I can, hopefully make things as clear as I can, so those of you who did get stuck solving this question can see how we can find the two possible edge lengths for that edge. So I'm rearranging this equation, our cosine rule, to solve for B. The first thing I'd like to do is to get everything onto one side of the equation. So the easiest thing to do is going to be to subtract a squared from both sides. Now I am going to write everything that we have so far on the left now, making a squared on the right to begin with, just switching around the two sides of the equation. So 2bc cosine of a is equal to a squared. The equation hasn't changed. I have literally just flipped it around because that's going to make it easier in a second. So I want to subtract a squared from both sides. So b squared plus c squared minus 2bc cosine of a minus a squared is equal to 0. Of course, a squared minus a squared is equal to 0. So we've got an equation equal to 0. Now if we rewrite this slightly, hopefully you're going to see where I'm going with this, because what I've noticed when I got to this point is we have b squared here. Of course, remember we're trying to solve for b. So we have a term that has b squared. We have a term that has b. And we have some other terms that are just constant values. They don't relate to b. So what I saw at this point is, hey, this equation kind of looks like a quadratic equation. If you remember back to volume 1, we took a detailed look at quadratic equations and how we can solve them. And those equations were in the form of ax squared plus bx plus c is equal to 0. Now, of course, in this case, we're not dealing with x being our variable. We're dealing with b as our variable. But it is in a similar format. We have some multiplication of b squared plus some multiplication of b plus some constant value is equal to 0. So allow me to rearrange this so hopefully it makes more sense. So in case those of you can't see how we've got these multiplications of b squared and just a constant value. So we have b squared, and here I'm going to add, and I'm going to add minus 2 times c times the cosine of a. I will explain where this is coming from in a second, multiplied by b. So I've taken our minus 2bc cosine of a, and what I've done there is I've rearranged this so that we take the 2, we multiply that by the c, then the cosine of a, and then by the b. Of course, the 2, we must recall, is a minus 2 effectively if we're adding minus 2. And I've put this in parentheses just to separate it from the b. So all this is, again, just to clarify, minus 2 times c times cosine of a times b is the exact same value as minus 2 times b times c times the cosine of a. It's the exact same value. All I've done is I've changed the order in which we multiply. We saw in volume 1 that we're free to do this. So I've removed the b from the multiplication here, and I've just put the b on the end. That allowed me to be able to separate everything else from our b term to get this looking more close to a quadratic equation. In doing so, I wanted also to have b squared plus, because if you recall, ax squared plus bx plus c, so I wanted a plus here, which meant I needed to make sure I had minus 2 inside the bracket so that this does still evaluate to the same. Because of course, if we multiply this out, we'd get a negative value here. If we add a negative value, it's the same as subtracting it. So hopefully you all followed that part. The other two terms that we need to, of course, make sure that we still keep is plus c squared minus a squared. If I put those in parentheses, set that equal to 0, you can see we do have an equation that's in the form of something times b squared plus something times b plus some constant term. Now again, we saw back in volume 1, these quadratic equations are usually written in the form of ax squared plus bx plus c is equal to 0. The first thing you're going to notice, again, we're not dealing with x, we're dealing with b. But the other thing you'll notice is that we can't use a, b, and c as the coefficients of x here, because a, b, and c are variables that are already in our equation. So because of that, and this may seem a little bit confusing, but of course variables are just letters. We can pick any letters that we want. So instead of writing ax squared plus bx plus c is equal to 0, I'm going to write db squared plus eb plus f is equal to 0. I've picked on d, e, and f because they're not variables that we already had in our equation. So if we write it in this form, that means that d is equal to 1 because we have 1b squared. E is equal to minus 2 times c times the cosine of a, so minus 2c the cosine of a. And f is equal to c squared minus a squared. Now we know the value of c, we know the angle a, and we know the edge a, therefore we can calculate the values of e and f using a calculator. So if we use a calculator, we can calculate the values of e and f. D is already known to be a value of 1. So this is equal to, well, let's bring up a calculator. So it's minus 2 times c. Well, c, if we recall, if I scroll back up, c, of course, is a length of 11. So it's minus 2 times 11, which of course is going to be negative 22, and that was multiplied by the cosine of a. A is 50 degrees, so it's minus 22 So I grab the calculator back. Minus 22 multiplied by the cosine of 50 degrees. So 50 cosine. The cosine of 50 is 0.642. That gives us that E is equal to minus 14.141327, and then some more numbers. Now, because we are going to be using this in a more complicated formula later on, I'm actually going to write this to more decimal places than I've ever done previously, and that's because we're not done working yet. We need to work with this value further, and so I don't want to simplify this down too much, because then we will introduce more inaccuracies in our result. So I'm going to write this as minus 14.141327. So minus 14.141327. C, or rather F rather, is equal to C squared minus A squared. C is 11, so it's equal to 11 squared minus 10 squared. Again, this is A because it is opposite our angle. Our angle is capital A. This must be edge A. Therefore, it's 11 squared minus 10 squared. So I'm going to bring up a calculator. Actually, we don't even need to use a calculator for that. What am I saying? 11 squared is 121. 10 squared is 100. That means it's equal to 21. So we have our value of D, we have our value of E, and we have our value of F. But why is this useful to us? Well, again, in volume 1, now I am going to take, I guess I draw a little box because this doesn't relate to the variables in our current equation. Please bear that in mind. The A, B, and C that I'm drawing in this box do not relate to A, B, and C on our triangle. This is just going back to the generic way of writing quadratic equations. So we saw in volume 1 that ax squared plus bx plus c equal to 0 can be solved using the quadratic formula. We saw how we can rearrange this equation to get the quadratic formula, and it's solved giving us that x is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. But that's when we're dealing with solving for x and when our coefficients are a, b, and c. In our case, we are not solving for x. In our case, we are solving for b, and our coefficients are d, e, and f. So what does that mean for us? Well, it means that x needs to become b, a needs to become d, b needs to become e, and c needs to become f. So that means we're solving for not x, we're solving for b. So b is equal to minus, our b becomes e, so minus e plus or minus the square root of b squared, so e squared in our case, minus 4, a becomes d, so 4d, c becomes f, 4df, all over 2 times a, again a becomes d. So in the terms of our equation, which is db squared plus eb plus f is equal to 0, this gives us the quadratic formula of b is equal to minus e plus or minus the square root of e squared minus 4df over 2d. It is the exact same equation that we saw in volume 1 in great detail. It is still x is equal to minus b plus or minus the root of b squared minus 4ac over 2a. The only difference is that we have changed the names of the variables in our original quadratic equation, and those changes must be reflected in the solution to that equation. So I'm just going to cross this out so we don't get confused. We're not dealing with this. We are dealing with this being our solution. The b is equal to minus e plus or minus the root of e squared minus 4df all over 2d. So just as we did in volume 1, the first thing we check is that this value here, which in our case is e squared minus 4df, we want to check that it's positive. If it's positive, we have 2 solutions, and we should be getting 2 solutions because there should be 2 different lengths for the edge of this triangle. So we're going to take our values of d, e, and f. D is 1, e is a negative 14.141327, and f is 21. We're going to plug them into this part of the equation, and we're going to evaluate e squared minus 4df. So that's equal to, well, e is minus 14.141327. We're going to square that, and we're going to subtract from that 4 times 1 times 21. So let's bring up a calculator. Fantastic. So we've got minus 14.141327, and I want to square that. So that gives us about 199.977. I need to subtract from that value 4 times 1 times 21. 4 times 21 is 84, so I'm subtracting from that value 84. That's going to give me 115.977, and I'm just going to say 9771. So 115.9771. So it's equal to 115.9771. So that is our value of e squared minus 4df. Because it is positive, we know we do have two solutions, which is what we were expecting. We know there should be two lengths for this edge, so fantastic. Everything is going as we expected it. So now that I've got e squared minus 4df, we can rewrite this entire equation as b is equal to minus e. Well, e is minus 14.141327. Therefore, minus 14.141327 becomes positive 14.141327, plus or minus the square root of our e squared minus 4df. We saw that's 115.9771, so 115.9771 divided by 2 times d. Well, we saw way back here, d is equal to 1, so 2 times 1 is 2, so divided by 2. So we can now use a calculator to work out the square root of 115.9771, so 115.9771. Square root of that is about 10.769, so 10.769. 10.769 before I forget that. So 14.141.327 plus or minus 10.769 over 2. We can use a calculator now to work out these values. So it's going to be 14.141327 plus 10.769 is equal to 24.910. Divide that by 2. And that gives us 12.46. So it's equal to 12.46. That's one of our lengths. Or it's equal to, if we clear this out, it would be 14.141327 minus 10.769. That's equal to 3.37. We divide that by 2. And that gives us 1.69. So the two possible values are 12.46 or 1.69. They are the two lengths of edges you should have got. So again, just to recap what we did here, the first thing we needed to do is identify which variable we're solving for in our cosine rule. Now again, we knew our angle is capital A in the cosine rule. That immediately tells us that the edge opposite the angle is lowercase a. So we knew that a has a value of 10. It's 10 units long. B and C are the other two edges. It doesn't matter which we pick. I just decided that we are solving for B, which meant that C was 11 units long. We then needed to solve for B. I did that by rearranging the equation to bring it all on one side and make it equal to 0. And then I noticed because we have a term of B squared and a term of B and some constant values, I could rearrange this into quadratic form. We saw in volume 1 how to solve a quadratic. Applying that but using the new names of variables we had in this form gives us the quadratic formula of b is equal to minus e plus or minus the root of e squared minus 4df all over 2d. We can work out the values of each of these various parts of our quadratic equation. We can plug those into the quadratic formula and we can use that to solve for b. So it's around 12.46 or 1.69, depending on how you wrote these values as you were working things out. Whether you stored them on the calculator or wrote them down on paper, you may have slightly different values, but around 12.6, or rather 12.46 or 1.69 are the two values that you are hopefully looking for. If you did get stuck at any point, really don't worry about it. This is perhaps one of the most complicated examples that we've looked at solving so far. Hopefully you got part of the way there, if not all of the way there, and hopefully my explanations now have shown you how to solve for an unknown edge when an edge is not opposite the angle that we know. So hopefully if you did get stuck, you now know how to apply the cosine rule in these kind of situations in the future. So with that, I really do hope that this video has demonstrated the true power of the cosine rule, and again shows just how versatile and useful trigonometry in general can be for solving problems that relate to triangles of any kind. So this is going to wrap up this video. Thanks a lot for watching, everyone.